So thank you for the introduction and thank you for attending my presentation. The topic of my presentation today is ensuring the service life of winding system in electrical machines at voltage up to 1500 volt. So the agenda for today is first the motivation and the vision, a basic approach, how to get into the theme. After that, the structure and comparison of the 2D and 3D JMAG model to get the electrostatic fields. And after that, evaluation of the electric field strength, the derivation of field lines and PDIVs. And last but not least, a summary and next steps. So when we start, what is the motivation and vision? To be honest, I think this picture is enough to say what's the motivation. We have a burned winding. We have some problems inside the air gaps. And that is the motivation. We don't want these failures to happen. And why are these failures happen? Because we increase the voltage up to 1500 volts. Normally, it's around 800 volts now, but like yesterday from AVL, we heard they're introducing 1200 volts, but 1500 volt is more or less the future. And also we have the switching frequencies from the SiC inverters, which have already a big impact to the theme. And you must also keep in mind the slew rates. So what are the other motivations? Of course, space reduction and cost pressure, like always. And we want to extend the life cycle. But what are the consequences of all these points? The insulation has a high stress level and it's designed on the physical borderline. And we have overshoot voltage, we have creep peak voltage, we have breakdowns, and of course we have partial discharges inside the winding and also inside the winding heads. And therefore our vision is to avoid this crucial damage and to get a better knowledge where the PDIVs happens and how we can prevent them. So what are the basic insulation coordinations? Normally you have 4 points for the criteria for an insulation system. Of course, the dielectric strength of the insulation system, the distribution of the field, the manufacturing process is very important, like when you have some cracks or air bubbles inside of the potting. And of course, it's sometimes forgotten the environmental influences, because you must keep in mind electrostatic phenomena always have a big impact from humidity, pressure, and sometimes oil compatibility. So what are the basic ways to reduce insulation stress? Of course, the easiest one is reducing the voltage at the motor terminals, because you must also keep in mind that we have an overshoot factor regarding the cable lengths, the supply cables, and so on. And of course, another easy way is improvement of the insulation materials, like of course PEAK or PAI insulation materials. And after that, we can show you the aim to reduce the control in the winding head, in the slot, outlet, and in the active parts. But how do we do it? We have a basic approach for this, and you can see it in this holistic evaluation cycle. First of all, it all starts with a winding design according to the standards with the creep pitch and the clearance distances. With this information, we can get all parameters to simulate an equivalent circuit for the winding, for the supply cable, and for the IGBT. With this information, we calculate the overvoltage at the motor terminal. And the important thing is the first winding, because at the first winding, you have the highest voltage level. Normally, the maximum is the doubled voltage when you have a really, really long supply cable and a really fast switching. In our case, or for this study, we say we have a factor of 1.4. When we calculate every equivalent circuit, we can go directly into the electrostatic FEA simulation to determine the critical location of the electric fields. So you can see, for example, no, you can see, don't see it, maybe it's a little bit small. There's electric fields here and of course here. And when we have the information about the distribution, about the maximum electric field strength, we can go into statistical evaluation of the partial discharge. Because, like I said before, it's a statistic phenomena. Sometimes it will happen, sometimes it will not happen. So I will show you later a diagram to prove that. So when we have the statistical evaluation, we can go further into the Paschen curves to take a closer look to the behavior. We use some Weibull distribution to check if everything is all right. And maybe we have to adjust the design a little bit. But when everything is fine, you must always test it with motor rates or formats according to the standard. Because, like I said, it's statistical phenomena. So when everything is fine, this picture should not be on your test grid, but normally something happens and we have to validate the simulation again and redesign of the insulation system. So how do we structure and compare the electric field inside the 2D and 3D JMAG model? For the comparison, we use an old IEV study which compared different hairpin configuration. Like you can see here, it's just 4 hairpins with a normal wire enamel with a material between slot liner and wire enamel, the slot liner, and of course the stator. But what we also done was we used the based on the winding scheme. We choose the slot with the highest potential difference inside the slot to get a worst case scenario, because normally you select or design the winding schemes that the potential difference is really small inside of the winding. But sometimes, like when you have short pitching, you have some bigger potential differences inside the slot and inside between the hairpins. And to evaluate the influence of the different insulation materials, we selected 144 cases. And what we changed was the voltage level. So we used 800, 1200, and 1500 volt. We changed the relative permittivity of the wire enamel to 2. That is more or less a future material. 3, that is peak or PI, and a standard PIE enamel with 4. The relative permittivity of the slot liner was also times 3. And what we consider was a gap between the slot liner and the wire enamel with 1, of course, air, and 3.5, which is a normal potting. Also, we change the gap in between. So we have a really small gap and a little bit bigger gap. And we also change the thickness of the wire enamel and the slot liner, just for the comparison. The good thing is, we heard a lot about 3D simulation, but for the electrostatic simulations, the 2D simulation is maybe a little bit better, because it has a simplified model structure, it's faster and more stable, and we can have finer meshes. As you can see on this picture, the mesh for the 3D simulation it's fine, but it can be finer. And for the 2D simulation, we can have a really, really fine mesh. And what we can see is the simulation time, of course, decrease. But what about the accuracy? In order to compare the 2D and 3D results, we selected 10 out of the 144 cases for further verification, and 3 of them are shown here. What you can see is that the difference between the 2D and the 3D model is almost nothing. And also between the 2D and the really, really fine 2D mesh, there are only some small influences. So what we can say is for our case study, the 2D simulation is faster, exactly, and of course we don't have the power like a Bosch with 1,000 or more than 1,000 cores, so it's easier for us to see the influences. And only to share some pictures. Here you can see the 3D, and here the 2D figure of the case 26. It has 800 volt, a permittivity of the wire of 3. So it's more or less a common installation coordination system. And as you can see, the maximum electric field strength is almost the same, and also the distribution inside the slot is more or less the same. So how we evaluate the electric field strength? Of course, we can use JMAG to get the information about the maximum electric field, the positioning of the electric field, and everything can evaluate in Excel or MATLAB. And for the wire animals, the slot line and the gap in between, the maximum electric field strengths are shown in this figure. On the first axis, you have the relative permittivity of the gap in between. It's 1 for air and 3.5 for a potting. We have the electric permittivity of the wire animal. We have 2, 3, and 4, like shown before. And with the different IEV colors, I hope you can see the differences. You see the spectrum of the maximum electric field strength inside the slot. But for a better overview, on the next slide, the single insulation material is shown. As you can see, for the wire animal, the influences of the other materials is not so high. But what you can see is that when we have air in between, the electric field strength maximum is not as high as for the epoxy. But why is it so? Because in the end, you have some field jumps when you have some different or high differences in the electric permittivity. So when it's more or less the same, the jumps are not so high. And therefore, when we know, for example, this picture here, the electric field is relatively small for the wire animal, we can be sure it's very, high for the gap in between. Because in the end, it's like the equivalent circuit of a film capacitor. So the electric field adjusts to each other depending on the relative permittivity. And on the last slide for the evaluation, you can see the slot liner. And for the slot liner, in the end, it doesn't really matter what is the relative permittivity of the wire and this wire animal. So we have no big problems inside the slot liner for this configuration. For a better understanding, I selected 6 cases to compare to each other. What are the differences? For all these cases, we have 800 volt, but we changed, of course, the relative permittivity of the wire animal and the permittivity of the gap. Everything else is equal. And what you can see, the combination of the relative permittivities of the different materials has a big influences. Like I said, for this case, we achieve a small electric field for the slot liner and the wire animal, but therefore the electric field inside the gap is really high. So we can take a closer look to cases like that one, which has a more homogeneous, of course it's not a homogeneous field, but a more homogeneous arrangement of insulation materials. So the first short summary: for every investigated case, the maximum electric field of each insulation component can be considered separately. We can say, okay, for case whatever, the slot liner is too high. For example, when we have a slot liner from with NKN, it has around 15 kilovolt per millimeter, but when we simulated 20 kV per millimeter, the case is not possible to use. So we can deselect some cases. After that, we see that the combination of different relative permittivity directly controls the electric field at the material boundaries, and a trade-off between the materials is a good idea to get a better overall insulation system. The next step is the second step is how we derivate the field lines and the partial discharge inception voltage. Why are we doing that? Because the knowledge of the position of the field strength is only one part of the insulation coordination, because normally the area where the highest electric field strength appears is not the positioning of the breakdown or partial discharge injection voltage, because normally it's in between two wires and it's more or less a homogeneous field. And therefore, when we can look into the Paschen curve, we have around 25 kV per millimeter before the breakdown. But when you have an inhomogeneous field, it's lesser. It's going down to 2.5 or 3.3 kV per millimeter, depending on the pressure, humidity, and so on. So what we can do is we can take a closer look first into the Paschen curve. There are two areas in this curve. First one is a short distance breakdown. For copper and iron is this area, and for PAE is this area. And it's more or less a good area for us, because there are not so many load carriers, and therefore no avalanche effect can happen, and we don't have breakdowns and partial discharges because there are no load carriers. But when we are in this area, we have many load carriers. We have the distance in between and the voltage, and some breakdown can occur. So when we are over the curve, we have definitely a breakdown. And what we can say is when we are near the curve or a little bit under it, we can consider partial discharge will happen. So how we get information about where the field lines are located, where are the critical areas? We can use JMAG Designer, and we can use the table results. The good thing is JMAG provides the electric field strength for each direction. So we have the X, Y, and Z. For our case, we only need X and Y. And we can use this information to go into MATLAB and interpolate and adopt it to a defined mesh, because, or defined grid. Because normally you don't have information about the mesh for JMAG isn't always the same. Even if you have the same cases, sometimes you have some little differences in between. So we gridded it to a defined mesh. And with this information, we have for every mesh point a defined electric field strength vector with a defined length, with a defined value. And therefore we can go along the electric field strength vectors to obtain the electric field lines. And with this variant, we know the voltage over the field line, or the potential, and the length. And with this information, we can go directly into the Paschen curve and see which are the critical field lines. Sorry. So how does it look? On the left side, you can see the vector plot of our information from JMAG, just gridded. In the middle, all of the field lines we calculated are inserted. But as you can see, there are so many, it's normally just black for you, I would say. And therefore, on the right side, we choose 25 worst case field lines. And as you can see, and as I mentioned, they are not in the middle, or not all in the middle, where the highest electric field strength appears. It's more or less here. But why is it here? Because the combination of distance and voltage, it's directly like in the Paschen curve, and we can consider a ratio when we increase the voltages where the breakdown will happen first. So we have done this for the already known 6 cases. In this slide, it's for an air between slot liner and wire animal. And as hopefully, as you can see, with a relative permittivity of 2, it's more or less, it's a corner of the hairpins. But when we increase the relative permittivity to 3 or 4, it more and more goes into the middle. So it always depending on the material mixer where the field strength is located. Where the field lines are located. It's the same for the epoxy or the potting. What you must keep in mind when I go back, here we have a maximum of around 15 kV per millimeter. And with epoxy, it's around 5. So our electric field strength is more and more not critical like before. And therefore, we don't have any problems in between. And all the critical field lines are located at the corner. For other cases, of course, there's also the possibility that the lines are more like that, but it always depends on the thickness of the gap, of the material mixtures, and so on. So with all of this knowledge of the maximum field strength and the location, how do we get a first impression about the partial discharge injection voltage? There are normally 3 basic ways for it. First of all is measuring with a standard. On the right side, you can see a measurement plot. And like I said before, it's a statistic phenomena. For example, in pulse 90, we have some partial discharges at, what is it? It's something under 1.5 kV. But after it, even if the voltage is higher, nothing happens. That's partial discharge. So what we can see also is, for a really high value of the voltage, we have every time some partial discharge. And when we go down again, there are also some partial discharge. So you must keep in mind, you have a really big statistical influence. Also, the inception voltage is not the voltage where the PD ends, because normally it's a little bit lesser. So you must be aware of it. And the other 2 ways to obtain the information about the partial discharge injection voltage is a simplified approach. We can see here, or taking advantages about the knowledge of the critical field lines from before. So I have a really big table here, but in the end, I think it's really easy to understand. We have 18 cases in total, but when you take a closer look, they're the same. The only thing which is different is the voltages from the inverter. We have 800, 1200, and 1500 volt. With this information, we can get an overshoot factor from our equivalent circuit calculation. So in our case, it was 1.4, and we have the voltage at the motor terminals. And with this voltage, we can go into our JMAG model and get the critical field lines and the ratio between the voltage of the critical field lines and the breakdown voltage of the Paschen curve. And with this ratio, we can calculate the breakdown voltage for the field line. That's the first step. And in combination with a safety factor, we can get a first hint about the partial discharge injection voltage. And as you can see, it's the same for every of the 6 cases, because the material mixer and the geometry is the same. So it don't depend on the voltage of the terminal in the end, where and when the breakdown happen. It only depends on the material mixtures. And as you can see, the different combination leads to different inception voltages. The next step is inside the standards, there is a calculation about the minimum requirement voltage. And in there's our aging factors, the overshoot factors, the input voltage, and a lot of other informations. And you can calculate it for 800, 1200, and 1500 volt. And you should never go near or below this value, because when we are under this value, we can say we have some partial discharges inside our system. So the last slide for the procedure is a comparison. And it's more or less, we see, for example, we suggest at 2600 volts, there are some partial discharges inside the system. And then we can compare it to the minimum voltage of the requirement of the standard. And as you can see, for 800 volt, it's way below. So this combination is practical for 800 volt. But for 1200 and 1500 volt, it's not possible to use it because we can be really sure that something happened inside. And as you know, when there's one partial discharge, after some time, everything breaks down. So in the end, we can compare each combination to see which combination are suitable. And as you can see, of course, when we have the same inception voltage for all cases, the figure and the table is the same. And what you can see also is when we have potting inside the slot, our breakdown voltage and partial discharge injection voltage is much higher. So we have a better or safer insulation system. And you must also keep in mind, when you have potting inside, the thermal aspect is mostly better than when you have an air inside because of the specific heat and everything inside of the system. So the summary and the next steps in the end. A method was presented to determine the electric field distribution in partial discharge for the active part. And the next steps is to adapt the procedure for the winding head and slot. To be honest, it's already done. But our next steps are adding temperature influences, especially for the potting, because normally you have only information about 20 degrees. So we have a potting for around 3.5. But when we have 180 volts, it goes up to 10 sometimes. So you must also consider your manufacturer and the use of the potting to get more information. After that, we have to add a material database, and last but not least, an optimization of the process to get really fast and solid information about our insulation system. Thank you for your attention.
Thank you very much. Questions? So, oh, one question.
Yeah, thank you for the presentation. In some cases, you showed that the main or the highest field strength was in the flat area between, so between pin and wall. Did you compare this with a simple analytical approach with like a Plattenkondensator?
And in the end, it's the same because you have the normal homogeneous field, and you can say it's depending on the literature and the measurement method, it's between 15 or 25 kV per millimeter for the breakdown. And the comparison we did was for this area, it's almost the same. So it's in the end, it's safer areas than the corner radius of the hairpins. But what you must also keep in mind is normally the winding isn't directly in the middle. So you have also the influences where the winding is located.
But in JMAG, you have this as well. So.
That's right.
Thank you.
Thanks for your presentation. I have two questions exactly. From your presentation number 23, the PPT, in which thermal range you have considered for the calculation of PDIV plus PDEV?
It was for winding temperature of 180 degrees.
Plus H configuration, right?
Yeah.
Okay. In addition, what is the best practice into select the coil liner and the coil insulation for the Paschen?
Normally for practice is what is the material with the lowest price, to be honest. And yeah, so that's the point. Normally you don't, for eMachines developer, it doesn't think a lot about the insulation system normally. I'm from the more or less high voltage or real high voltage up to more than 1 million. And in the generator factor, you have some really big knowledge about the insulation system, so you can use, for example, mica tape or something, but it's not possible for the automotive industry because of the roundings and so on. So I think this presentation and the whole topic is more or less interesting for the automotive industry, but it will take some time to adopt it.
Yeah, quick question. Thank you for your presentation. Very nice presentation. Just a quick question about the aging. Did you include it in the aging of the materials, for instance, the slot liner or the enamel?
I think you have the same question yesterday. I'm not sure, but we must look behind to JSOL to adopt it inside of JMAG. It's the easiest way, but what we can do if we have a lot of measurements, of course, we have some lookup tables or anything like that to get more information about it.
Anything else? Yes.
So these Vmin levels that you get there from these equations, I suppose they're the requirement to meet when the motor comes from production. How about taking into account aging of the materials in there? Is that also something you're considering?
Yes, it's the minimum voltage which is described.
Is that with your aging factor?
Yeah, it's aging factor according to the standard.
Okay, so you just apply a factor basically.
Yes.
That represents.
Yes.
Okay.
Because like I said before, in the automotive industry, we don't have so many informations and testings to get a really huge database.
Okay, thank you.
In your field analysis, I guess in the conductors, you're not using any current in your simulation, just a potential. But if so, could you give a comment of what happens with the breakdown when you have a really high current and also then a really high magnetic field in those gaps?
To be honest, you're right. It's only with the voltage at the moment, but what will happen when we have a breakdown with high current? Of course, everything is destroyed, but we must take a closer look to it. That's a good point.
Okay, thank you. So thank you for your presentation, Philippe.